Good morning. So, I will continue today with the second topic, that is wide band gap semiconductor solar cell or thin film solar cell. And what we have discussed in the previous lectures are that it's the silicon solar cell which actually used a lot in the technology or in real practice, had certain disadvantages. I will again discuss a little bit about that in today's lecture. And then the requirement of a wide bandgap semiconductor solar cell or thin film solar cell was felt by the community, and then the first material which they have chosen to make a successful solar cell for practical use was CDT, cadmium telluride, and then we have discussed detailed about how to use CDT in a solar cell, making a heterojunction of CDT CGS, CDS. There are other compound semiconductors also, or wide bandgap semiconductors also, which are being used as semiconductor solar cell or wide bandgap semiconductor solar cell, which you can find in the literature. So, today what I will do, that I will try to review this CDT, CDS and CIGS CDS solar cell with some question, and also finally we will look at some chapter review question or frequently asked question about these two solar cells. So, let me first ask again this question, that how efficiency of a solar cell varies with band gap, and then we will come to what are the disadvantages with silicon. So, as we have discussed that if we plot band gap along x axis and efficiency along y axis, this is a typical plot which we get. And if you look at this particular plot, then here we have germanium, then silicon, their lower band gap, then relatively higher band gap indium phosphide, gallium arsenide, cadmium telluride, CDS. CDS is the highest band gap, as shown here. Now, the question is how it is important to look at how efficiency varies with band gap. So, if we come from say germanium, silicon and towards a higher band gap material or wide band gap semiconductor material, we also see that there is a change in the band gap, not only in magnitude, but also the structure of the energy band. Like silicon is an indirect band gap material, whereas cadmium telluride is a direct band gap material. So, this is one important issue. But as far as efficiency variation with band gap is concerned, this is a typical variation. And then actually you know that when we look at the lower band gap material like silicon, what we expect that more light can pass through the silicon, although it requires a thicker wafer, and it also gives us higher current in the solar cell or higher short circuit current density, but with low VOC, because the band gap of silicon is less. So, we have to go to higher band gap. So, higher band gap, if we come to CDT, it is around a band gap of 1.5 electron volt. Okay. And then because of higher band gap, the open circuit voltage increases. Okay. So, CDT is somewhere actually in between, so which is around 1.5 electron volt, which is a very good optimum band gap for solar cell. But you know, for silicon there are some other problems, like it is indirect band gap material. That means, when we plot an energy wave vector diagram, EK diagram, then this is the conduction band and this is the valence band. So, the conduction band minima, which is here, does not align with the valence band maxima, which is here. So, that is indirect band gap. So, therefore, the absorption of light in silicon is less, absorption coefficient is smaller, and therefore, we need a thicker silicon wafer. So, typically if you see that the silicon wafer is few hundred micrometer thick, which are used in the solar cell, and that actually requires a lot of the fabrication process. I have already discussed about this fabrication process in topic 1 of silicon solar cell, and we have seen that the fabrication process is quite involved in case of silicon. Okay. So, therefore, it is not only it is the involved method, but also the cost goes high. But of course, if industrially, if we have more acceptable material, then what we have, we have to see the cost per dollar or the per watt per dollar, that is how much power is delivered for $1. In that way, silicon gets an optimum, but of course, the thickness of silicon cannot be reduced because of its lower absorption coefficient. On the other side, if we consider CDT, which is direct band gap material. So, if this is silicon and this is CDT, its conduction band minima and valence band maxima they are in the same point. Okay. So, therefore, the absorption is very good and it is also wide band gap, and the thickness of the absorbing layer, that is CDTO, is drastically reduced. Okay. Although there is a technological challenge like CD is toxic and there are fabrication process like silicon, it is well established, and also the physical properties, these are issues. But of course, because of this, you drastically reduce the thickness or drastically reduce the amount of material used as the solar cell. So, this is the advantage of CDT to be used as solar cell. And if we just look at the journey of this solar cell, okay, before that just let me mention the CDS, whose band gap is quite high, 2.3 to 2.4 electron volt. If we make an heterojunction with CDT, then it gives a very good choice, which we have already discussed. Now, let me again come back to this issue, that what was the journey of CDT CDS solar cell. So, it starts in 1950, where the research on material has started in 1950s, that means cadmium telluride material. Okay. And almost 20 years later, around 1969, the first CDT cell was fabricated in the laboratory. And then again, almost after 10 years, a CDT cell with efficiency more than 10% was demonstrated. So, there is a progress. If you come to 2009, CDT solar cell reach, this is what I mentioned, the cost per watt, CDT solar cell reach $1 per watt. So, that means it is industrially viable. And in 2024 here where we are now, that it has an efficiency, module efficiency of 19% or higher. So, it is now a mature technology. So, some more work probably was needed in order to improve the efficiency, and work is under progress, but of course 19-20% efficiency is good in terms of that when it is in the module. So, therefore, there are real application of CDT CDS solar cell. Now, let me come to the second question: why CDT film of thickness few micron is a good material for solar cell? So, that I have already addressed because of its higher absorption coefficient. CDT has very high absorption coefficient as compared to silicon. So, if we have a material which is having higher absorption coefficient, we can choose a very low dimension also. Low dimension in the sense only few micrometer is good enough in order to make the solar cell. Okay. Now, second is what are the possible dopants of CDT? I already mentioned during one of my lecture that when we make a solar cell, it is important that we make a p type and n type because they are all junction solar cell. In this case, it is heterojunction CDT CDS. In case of silicon, it was homojunction, that means p type and n type both were silicon, and here p type is of CDT is used and n type CDS is used. But how to make p type and n type choose p type and n type dopant from CDT? So, let us look at this periodic table again. So, you can see this is cadmium here. Okay. So, look at this, the material which is the cadmium, it is in 2B. So, if I look at the 3A elements, then aluminum, gallium, indium, etc., they can be doped and make it N type. So, replace cadmium by aluminum, gallium, indium is 3 and make it N type, or this is tellurium which is 6A element. If we want to make it N type, we have to dope it with fluorine, chlorine, bromine, iodine, etc. So, this way we make N type CDT. If we want to make a P type CDT, then again if we look at cadmium and then we look at the elements which are at 1B, so that means copper, silver, gold. If we dope copper, silver, gold in cadmium side, then it becomes P type, all right. And if we do phosphorus, arsenic, antimony, which are 5A element in the tellurium side, then also it becomes P type. Okay. So, these are the elements which we can choose to make P type and N type cadmium telluride. But what people have noticed, that which I also mentioned, that if you create a vacancy in cadmium telluride, it becomes an intrinsically P type material. So, lot of calculation are going on, and one need to look at the theoretical model, that how it shows the P type conductivity. Okay. In the literature, I am not discussing in detail here, but a vacancy can make it P type. Okay. Let us come to the next question. Draw the schematic of CDT CDS solar cell. What are the advantages and disadvantages of this heterojunction? So, we have already seen how this how the solar cell schematically. So, you start okay. I use multiple color for the different layers. So, the top we have the substrate or superstrate, okay, and then we have a TCO layer, okay. Generally zinc oxide is used as TCO, and then we have a thin window layer which is CDS, then followed by our absorber layer CDTE, and then this is the back contact. Typically molybdenum is used as back contact. Okay. So, typical thickness of TCO is around 200 nanometer. CDS layer is very thin, say 50 to 80 nanometer. CDT, which is actually the active layer, is relatively thicker, say 1 to 2 micrometer, and back contact, that is molybdenum contact, is also few micrometers, say 1 to 2 micrometer. Okay. So, this is the architecture of a CDT CDS solar cell which we have discussed, and we know that what are the function of each layer. Okay. Particularly CDT and CDS, they form the heterojunction. In between CDT and CDS, the junction is formed which actually act as an active junction for the functioning of the solar cell. Okay. So, let us look at what are the advantages and disadvantages of this heterojunction. So, if you remember that we discussed in one of the tutorial session that what is the importance of homojunction and what is the importance of heterojunction. Okay. So, one advantage with heterojunction is that you can have a capability of tuning the solar spectrum which is falling on the solar cell and is getting absorbed because of two different band gaps of two different materials like here CDT and CDS. Okay. Whereas in homojunction there is no variation of band gap. Suppose I considered silicon homojunction, it is only silicon for both p type and n type having exactly same band gap, and therefore, the tuning of the solar spectrum which is allowed to fall and getting absorbed in the solar cell is not possible. All right. So, this is one advantage, and therefore, what people have observed for CDT CDS particularly, we have to also remember that CDT CDS are not very well matched lattice, okay. But still it gives quite a high current density, large current density, okay, and that actually give higher efficiency. And therefore, the CDT CDS junction is so important. But there are of course the disadvantages, because as I mentioned that the lattice mismatch is high for CDT and CDS, and therefore, there are interface states when you grow these two material which acts as a defect center. Okay. And therefore, there is more recombination. So, we all know that I have already discussed with you what are the recombination process, and then CDT CDS actually gives a having more recombination because of lattice mismatch. Apart from that, also there are other defects which causes more recombination. All right. And of course, when we grow two materials, we need two different techniques to grow. So, therefore, as far as the thin film techniques are concerned, we need more techniques in place in order to make a proper CDT CDS junction solar cell. Okay. But anyway, there are the advantages which I told, and therefore, that it has taken a journey which I have shown in the previous slide, that up to now it has been shown that almost 19 to 20% of efficiency in the module, which is quite promising and quite good. So, now let us look at the next question. In CDT, CDS, sometimes bilayer CDS is used. Why? Bilayer. Okay. So, what we have seen, when we grow it layer by layer, as I shown you, that on top there is a superstrate, okay, and then let me again draw it. So, this is superstrate, and then after that we have TCO, then you can have two layers of CDS, CDS one layer, then you have relatively thicker CDT layer, followed by the back contact. Now, the question is why the two layers of CDS are sometimes used, or bilayer CDS is used, but you do not change the thickness much, keep the thickness of say approximately 80 nanometer. So, it is thin. So, there are a lot of the transmittance of photons when it comes to the solar cell, because of it is quite thin, of say 50 to 80 nanometer range. But with this advantage, when we grow two CDS layer, what actually is been seen, that it make a very good continuous layer. Otherwise, what happen, that there is always a shunting path from TCO to CDT through CDS. If it is not grown uniformly, if the grains are not grown properly on the substrate, okay, of CDS film, then the problem is there are some kind of pinholes, there are some kind of discontinuity on the structure, which actually allows CDT and TCO to be in touch with each other. Okay. So, therefore, it gives a very good the process to make a solar cell with these two layer, so that the problems related to the shunting paths are removed. Okay. So, this is why people sometimes use bilayer of CDS in CDT, CDS solar cell. Now, we come to another question. So far whatever the architecture I have shown in CDT, CDS solar cell, they are all exactly like thin film, one after another layer you grow, take a substrate, grow TCO and then CDS. If you make bilayer, then it is better, and then CDT and then make a contact. Okay, these are all by thin film technology process. But now it was shown by Fan et al. In 2009 that if we grow CDT, CDS nano pillar instead of this planar film, it demonstrate better efficiency, okay, and it was published in Nature Material. And what are the reason? So, if you look at now the architecture, so it is same as the superstrate which we have discussed in case of planar, and then a copper aluminum contact, then here it is in the opposite state. So, this is CDTE, and then they have grown it on anodic alumina template. AAM, and now you can see the CDS, which is grown as a nanopillar. Okay. So, now question is what is the advantage of that when we grow such structure? The advantage is, when we grow a nanopillar kind of structure and not a continuous film, we have a better transmittance, okay, because the dimension of the nanopillar is quite small. So, we have better transmittance. You can look at these SEM images, this is anodic alumina template, and then these are grown nanopillars. Okay. So, one advantage is that we have a better transmission of light because of its lower dimension. It gets more space to get transmitted, and second is absorption is also higher because they are small dimensions. So, there is a quantum confinement effect. So, due to quantum confinement. I will discuss about quantum confinement effect in detail when we will go to the next topic in quantum dot sensitized solar cell, but very simple way, if we want to understand what is quantum confinement, you can just consider the particle in a box. Okay. And generally, if we solve this particle in a box problem by quantum mechanics, we see that the energy is inversely proportional to the dimension or the width of the quantum well. Okay. So, now if we reduce the dimension, the energy eigenvalue increases, which gives a higher split in the energy between two levels. So, eventually this confinement of charged particle inside the quantum well separates the conduction band and valence band to higher value and giving rise to higher band gap. So, that is called quantum confinement, which immediately enhances the absorption of light. And third point is better electrical transport. In this direction, because they are all nanorods which are forming. So, you know that electron which is flowing through the circuit, if there is a plane and there is a rod, it will always find the easy part towards the in the rod, and therefore, it gives a better electrical transport. Okay. So, we go to now the next question. Show heterojunction CDT CDS in the energy band diagram with ZNO layer on the top. Okay, fine. We have already discussed ZNO as TCO, but let me again draw it. So, when you draw a diagram, something like this, there is a step here. Okay. So, this is conduction band, this is valence band. Okay. So, now this is CDT side, whose band gap is around say 1.5 electron volt. Okay. And then you come to junction with slightly higher band gap, which is CDS of say approximately 2.2 electron volt. All right. And then you come to third layer, that is ZNO, whose band gap is approximately 3.3 electron. They are not at this scale, but this is what I would like to show in how this junction forms. So, the advantage with this junction is that lot of light gets transmitted through zinc oxide. So, it really works it because of very large band gap, it really works as a very good window. Okay. And eventually, this is a junction region where photon crossing the zinc oxide layer comes to the junction and make it an efficient solar cell. Okay. So, we go to the next question. What is CdCl2 activation? How does it improve the performance of a CDT CDS solar cell? So, I have already discussed about the CdCl2 activation. Let me again highlight this with this example. So, you can look at this particular SEM image and look at this particular SEM image. Okay. So, this is the as grown CDT and this is activated CDT. There is a huge difference between the morphology or the structure of these two. Okay. So, if you look at the top one, the grains are quite small. Okay. And look at the bottom one, which is activated, the grain actually has grown up. Okay. And which is required because for a better transport and hence a better efficiency of the solar cell, you need to have a very well grown film. Crystalline or polycrystalline growth should be very well the developed grains. Okay. And that is just by annealing process of CDT one could not achieve, and the efficiency remains much less as compared to what one should expect from a solar cell, and this particular process enhances it a lot. So, how it is done? Initially the way people have started doing it, that they put this CDT in some chlorine compound and then used to heat, so that some chlorine goes inside CDT and activate it. But later people realized that there is certain problem because some toxicity and other issues come. So, what they did after that, they coat a very thin CdCl2 layer on top of CDT and then they anneal this, okay, heat it up, and therefore, what happens, this chlorine get dissociated, it goes inside CDT and then it changes the vapor pressure, and because of that there is a grain growth. So, well oriented, well structured polycrystalline films start forming, or recrystallization of CDT takes place, and that is what we see in the real SEM images, and then there is a huge increase in the efficiency. So, the next question we will see exactly how this the efficiency or the typical IV spectrum varies when it is activated and not activated. So, please look at this one. So, the top one you can see this is CDT, CDS, FTO, this is another the transparent conducting oxide and glass. This is the architecture and this morphology is shown here, and this is typical IV characteristics corresponding to this. Okay. So, now the next one, so as deposited air annealed CDT, this is the first one, okay, and this is the activated one. So, this is as deposited, the first one, the second one is air annealed, so we know that always when we would like to grow the grains or make it a well grown the polycrystalline material, we generally do annealing. So, this is the air anneal and this is actually CdCl2 treated. So, now you follow these three graphs. So, when we have a as grown CDT, this is a typical IV curve where you can see from the graph itself you can see the current density is close to 20 milliampere per centimeter square, and the open circuit voltage is around in between 600 to 700 millivolt. Now, when you air anneal it, it deteriorates, the current density is deteriorated, okay, which was approximately 20 is come to less than 20, from 16, 17 milliampere per centimeter square. So, why it is so? So, suppose you look at the morphology which is there in the left hand side. See, as soon as we air anneal it, of course, there is a growth in the grain. This is standard procedure, but then there are some pinholes you can see located here, here, some kind of cracks, pinholes is developed. And I told you that this is not good for a solar cell, because it completely touches to disturb the entire transport of electron, and then it creates a shunting path, eventually reducing the current density, and this is what is happening. Although open circuit voltage does not change much, all right, but there is a definitely inferior IV characteristic as compared to the top one or the as deposited one. Now, we come to CDCl2 treated CDT, and now you can very clearly notice then how the grains are developed. Grains are grown, okay. It's make a very well grown polycrystalline CDT material, okay, and immediately you see a huge improvement, significant improvement in the IV characteristics, okay, leading to a current density of almost 25 milliampere per centimeter square, and then even enhancement in the open circuit voltage also. Okay, because I have already discussed that what are the parameters that decides the open circuit voltage when it is in a cell. Okay. So, you can look back to those discussion where I mentioned where open circuit voltage is higher. It is not only the band gap, but some other factors also which actually improve the open circuit voltage, and this work was done by Bai et al, and this nicely demonstrates that three stages, that as grown air anneal and CDCl2 activated, and there is a huge enhancement in the IV characteristic in terms of short circuit current density, in terms of open circuit voltage, and therefore, a better fill factor as well as a higher efficiency. Okay. So, when we come to this one, I should write that short circuit current density enhances, open circuit voltage also enhances, fill factor is also enhances, and finally, the efficiency also enhances. And that actually was incorporated in the CDT CDS solar cell technology. Okay. And then actually it found the real promise of this particular material of this particular solar cell to be used in the industry. Now, I come to next heterojunction solar cell, that is CIGS material, which is in active material. So, it is architecture wise it is same. Okay. So, you have substrate, and below that you have TCO, and then you have CDS again, okay, and then CIGS instead of CDT. Okay. It is a relatively thicker layer of CIGS and very thin layer of CDS, and then followed by a contact. Okay. So, this is a standard architecture which we have used in case of CDT CDS, the same one which is for CIGS CDS, and I have already discussed a lot about this particular architecture also. So, the question is why a range of wavelength can be absorbed. Okay. So, it is again simple, because you know that the CIGS is a material which is a combination of CIS and CGS. Okay. So, depending upon the stoichiometry of copper, indium and selenium which is used in CIGS, its band gap can vary from CIS to CGS, which is from few 1.5 electron volt to almost 2.2, 2.3 electron volt. There is a huge range of band gap which you can cover just by changing the the composition or the stoichiometry of the CIGS film. Okay. And therefore, it almost covered 300 to 1300 nanometer range of wavelength. All right. And there is the advantage of using the CIGS as a material in the solar cell. So, when it is generally grown, it is grown on either soda lime glass or polyimide films. Okay. So, there are certain importance of using soda lime glass, and soda lime glass I will show it in another question. The sodium goes to the active medium and it also improves the transport or electrical characteristic of CIGS. So, if you grow it on soda lime, that because of the sodium going towards the active medium like in CIGS, you can have a better electrical characteristic, and if you grow it on polyimide films, you can make it a flexible solar cell, and people have demonstrated how flexible CIGS CDS can be made using a polyimide substrate. Now, I come to the real architecture of the CIGS CDS solar cell. So, if you look at this, okay, so there are several layers of CIGS CDS solar cell which I have already discussed, but let me again look at all these layers and their use. So, the anti-reflection coating magnesium fluoride is used, which is typically 75 to 125 nanometer, and light falls from this direction. Okay. Then you have an aluminum doped ZNO which is around 300 nanometer. Okay. So, we know that what is the use of anti-reflection coating at the top. Okay. It minimizes the reflection, so that the more light goes inside the solar cell, and then we also know that what is the importance of the TCO. Here the TCO is aluminum doped ZNO. Okay. And then high resistive ZNO of 100 nanometer. This is a very important part in this solar cell, because if you use a high resistive ZNO in between, which is this layer, then what you actually do is basically again this problem. I told you that there is always a chance that because these are all thin film configuration. So, there is always a chance to create a shunting path, okay, with the TCO and your layers where the semiconductors are used, and that actually disturbs the solar cell or disturbs the electrical transport, and therefore, a high resistive ZNO of 100 nanometer is grown. And then as usual, the CDS window layer of 40 to 80 nanometer, which is N type, and P type CDS, which is an absorber layer, typically 1 to 3 micrometer is used, and then moly back contact 1.5 to 2 micrometer. And then as I mentioned that it is either grown on soda lime glass or polyimide substrate. Okay. So, there is a total configuration of a typical CIGS CDS solar cell which people have demonstrated. Now, again I come back to this point that as I mentioned that it is grown on soda lime substrate, and if you look at this particular, that the sodium, how sodium goes from here and it goes actually inside the network of CIGS. Okay. And it improves the electrical transport, and it also improves in terms of grain orientation. It also leads to some sort of segregation of indium and gallium. So, therefore, this is actually a very important the element which is required to grow CIGS material. Something like that in CDT I told about the CDCl2 activation, and here you get is kind of activation from the substrate itself, where soda lime substrate, the sodium goes to the structure of CIGS and it improves the property. Now, I come to the last point, and this is related to different deposition of CIGS. All right. So, I discussed in my lecture different processes which are used to grow CDT, CDS and also CIGS. Some of them which are generally used for growth of CIGS, let us just compile. So, one technique which is very common called co-evaporation technique. So, this is a well established technique and for lab scale devices. This is the advantage, but what is the disadvantage is? Disadvantage is that simultaneous control of sources, because you know that CIGS, copper, indium, gallium, selenium, the 4 sources you require for simultaneous evaporation, and therefore, the simultaneous evaporation of the sources are quite often they are difficult, and therefore, in order to maintain the stoichiometry. So, I told you the stoichiometry is extremely important in case of CIGS, and therefore, maintaining a stoichiometry while simultaneous evaporation is a difficult task, and you may not be having a good reproducibility over a large area. Generally, the solar cells are grown on large area, maybe for lab scale, for small scale you can maintain the composition, you can maintain the stoichiometry, but when you grow it on a large area for a particular solar cell, and this is a real issue. Now, second technique is sputtering. We also have discussed about the sputtering process and how films are grown by sputtering, and this is the main advantage is that in the sputtering you can have a good control of the deposition parameter. So, you can have a better control of deposition rate and as well as a good crystallinity. But if you look at a sputtering technique, it involves lot of things. You know that you need a sputtering the chamber, you need almost like high vacuum condition and sometimes better than high vacuum condition, and also you need the sources, the power sources for sputtering. So, therefore, it is having higher operational cost. And another thing is that sometimes it produces multiple phases, multiple phases like either CIS or CGS. So, they are sometimes phase segregated and they are not properly grown as a material like total CIGS. Alright. So, this is the disadvantage of sputtering, and the third technique is selenization or sulfurization. So, what are the advantages of selenization? This is actually used for large area deposition. So, the most important aspect is for large area deposition we choose this particular technique, and this is also an established technique for this deposition process. All right. And it can be also used for precursor deposition and reaction. But what are the disadvantages? Disadvantages are that you use toxic gases like H2SE, and some additional processing deposition steps are also required, and there is an issue with the poor adhesion of this film. The last one, which is also widely studied, are electrodeposition. The main advantage of electrodeposition is that it is low cost and also it is a room temperature deposition. So, it is very simple deposition with low cost and room temperature deposition, but when we want to make a proper film in a large area, process optimization is quite difficult in case of electrodeposition. So, these are few advantages and disadvantages of different techniques. It will depend who wants to grow these films and for what purpose, one is to look at or study the literature or the real the activity which are going on in the different industry and see how people are really growing these films and for what purpose, and therefore, a clear idea about the comparison between all these techniques should be there in mind. Okay. So, okay. This is of course a very important thing. Finally, what we have to look at that what are the factors that actually influence the efficiency. Okay. It is a very general question and not only for CIGS, for a general solar cell, what are the factors that influence the efficiency. So, we would always like to have a higher short circuit current density, we would always like to have a better open circuit voltage and higher fill factor for a better efficiency. Okay. So, for a higher short circuit current for a given illumination condition, that means for a given power of the sunlight or whatever source we are using, one has to be very much careful about the transport of charges. It is not only that the charge carrier generation, but also the transport of the charges across the solar cell, and so that the charges can not only be separated, but also can be transported properly with minimum recombination and giving rise to higher current density in the outer circuit. Okay. So, this is the first point, and second is of course that VOC. I told you that the open circuit voltage, and for that you need to grow a material of well developed or well grown crystallites inside the active medium. Okay. And therefore, you can have a band gap which is the more defect free, and you have a proper the band gap which is with less recombination process, because we all know that if there are defects, okay, or there are lot of grain boundaries or lot of interface states, they they disturb the transport, the enhance the recombinations, with all these quantities should be reduced, eventually giving rise to higher open circuit voltage as well as the short circuit current density and with a higher fill factor and efficiency. So, these are few things which we need to remember, okay. And particularly in case of CIGS, the optimization of material is extremely important, CIGS, because this critically depends on the composition or the stoichiometry, and therefore, one has to choose a deposition method also in such a way that you can actually make your film or make your material for the solar cell well optimized for the band gap which you are looking for, okay, and this should be reproducible. So, this is another very important factor in order to improve the performance as well as the efficiency of the cell. Now, let us review the chapter with some frequently asked question in case of CDT and CIGS, CDS solar cell. So, what are the major problems with silicon PV technology? So, I mentioned that in silicon PV technology, the major problem is that silicon is indirect band gap and therefore, absorption is less, you need higher thickness, and therefore, the fabrication process up to industrial scale is quite involved. Okay. So, these are the problems. Second is how efficiency of the solar cell varies with band gap, that also you have seen that efficiency varies with band gap, it has a peak and then it falls, okay. And CDT is somewhere which is in the optimized close to the peak efficiency, and then it falls when we have higher band gap. So, when we have lower band gap material, we have higher current, when we have higher band gap material, we have higher open circuit voltage, and CDT is very close to the maximum, and therefore, it is an optimum material for a solar cell. What happens when photons energy is greater than, equal to, and less than band gap of this cell for junction solar cell? So, that I discussed in the previous lecture also, that when we have the photons which are having energy more than the band gap energy. they actually excite the charge carrier from valence band to conduction band, and then when it's comes back to the edges band edge, then there is a thermalization loss. When the photon energy is equal to the band gap energy, it can absorb very efficiently, because it takes up one electron from valence band to the conduction band, and by this process the photon get absorbed. When its band gap is less than the band gap energy, then it is transmitted. So, the transmission loss is high. Fourth question, why few micron thick CDT is a good active medium for solar cell. So, this also we have discussed that we go from silicon to CDT, that means we go from one technology, that is thin or bulk material, to a thin film technology, and this was only possible because CDT has much higher absorption as compared to silicon, okay, and therefore the thickness of the material drastically gets reduced. In case of silicon solar cell, where we used more than 100 micron thick silicon, in case of CDT we just need 1 to 2 micron thin CDT, because its absorption coefficient is almost 100 times higher than silicon. In CDT, CDS solar cell, p type CDT is used. How p type conductivity is achieved? So, we have discussed that how p type conductivity is achieved. You can create p type conductivity by replacing cadmium. You can also create p type conductivity by replacing tellurium with appropriate elements which are there in the periodic table. So, now make a schematic of CDT CDS solar cell and explain role of thin CDS layer. So, we have already drawn the CDT CDS schematic. The role of CDS layer is very important, because it not only forms the active junction with CDT, but also it acts like a window for photon to be transmitted and falling on the junction because of its higher band gap. Okay. So, it has an advantage of having higher electrical or the current density for a better transport, as well as also the photon falling to the active junction through the CDS window, and is very thin. Okay. Therefore, the light passing to the active medium, that means the heterojunction which is formed between CDT and CDS, is quite efficient. So, now draw energy band diagram of a solar cell, CDT CDS solar cell with a ZNO layer on the top, okay, that I have already shown. That in this case I have first a CDT layer which is having lower band gap, then I go to the junction, and then junction is with CDS. So, it enhances little bit the band gap, because CDS is having higher band gap, and then it goes to third layer, that is zinc oxide layer. The band gap is further enhanced because its band gap is 3.3 electron volt, and therefore, as far as the light absorption or the transmission of light is concerned through ZNO is much higher as compared to other junction solar cell which we do not have this window option. Okay. Now, what is the role of CDCl2 activation? So, we have seen that CDCl2 activation is extremely important. If we do not do CDCl2 activation of CDT in CDT CDS solar cells, generally the parameters are quite poor. Even if you would like to anneal them, what we have seen, it is very clearly demonstrated that they even further reduced. Okay. Because with annealing, although the structure grows little bit, the crystallites are grown, but there are a lot of the pinhole formation, there are cracks, etc. So, therefore, the performance of the solar cell decreases just by air annealing, and therefore, it is extremely important for CDT CDS solar cell, or the solar cell where CDT is actually the absorbing material, to improve the crystallinity. In order to improve the crystallinity, CDCl2 activation is done. And what we have seen is that as soon as we do the CDCl2 activation, then immediately there is a growth of crystallite, okay, and because of that we have very good short circuit current density as well as the open circuit voltage. Okay. So, this was demonstrated in one of the example, and therefore, CDCl2 activation is extremely important, and the grain growth takes place because when we do the CdCl2 activation, there is a change in vapor pressure which eventually leads to better grain growth of CDT. Okay. What is the range of solar spectrum that can be absorbed in CIGS as an active medium? So, I told you, because in CIGS it is copper, indium, gallium, selenium. Okay. So, it depends very crucially on the stoichiometry or the composition, and one can very critically vary this composition from one particular, let's say CIS, where gallium is 0, to CGS, okay, where indium is 0, and one can tune a wavelength of 300 nanometer to almost 1300 nanometer in one particular CIGS. What is the role of TCO on top of an NCDS? Okay. So, TCO is extremely important, because we know that in this case, say aluminum doped Zno, which we have shown in case of a particular CIGS CDS film architecture. So, it has two purposes. One is that it makes a window for light to go, because it is having higher band gap. So, light goes through that window, and second is as it is transparent, as well as as it is conducting, it gives a very good conducting path of electron, okay, and therefore, the TCO is extremely important, or it is an integral part of this type of solar cell. Okay. So, in the back that we have a metallic contact, molybdenum contact or other contact like gold contact, but the top, where if we cannot make a metallic contact, we need a transparent window as well as a very good conductivity, and therefore, transparent conducting oxide material or TCO materials are used. Okay. So, in the next we will start the new topic in my next lecture. So, the discussion on CDT, CDS and the chapter review is over today. Thank you.